Welcome everyone to today's chaos, and our speaker today is Professor Marvin Geller, who is on our faculty, and many of you have taken his atmospheric dynamics class, MAR 594, which he teaches every spring, and he will do it again next spring. And if you haven't taken that class as yet, I recommend it highly. And this semester in the fall, he's teaching ATM 102, which is a freshman class in meteorology, and he has 200 students in that class. And but I want to tell you something a little bit more about his very distinguished background. So Professor Geller was the director of ITPA for 13 years, and then after that he served as the dean and director of SoMAS for 5 years. And before coming to Stony Brook, he was head of the Laboratory for Atmospheres at Goddard Space Flight Center in Greenbelt, Maryland. And prior to that, he was a professor of meteorology at University of Miami in Florida. And he is a fellow of the American Geophysical Union and also a fellow of the American Meteorological Society. And he served as president for the Scientific Committee for Solar Terrestrial Physics for 7 years. So, one of the most amazing aspects of Professor Geller's contribution, in my opinion, is the tremendous effort and energy he has spent in the service of science and atmospheric science in this country and worldwide. So throughout his career, he has been an advisor and then senior advisor to the National Academy of Sciences, to the American Geophysical Union, and there are so many panels, the American Meteorological Society and NASA, and in so many diverse ways that it would be difficult. I mean, it would take me an hour to describe. And just to give an idea of the range of the capacities that he has served in, he was chair of the Board of Governors of New York State Sea Grant for a number of years. And he was among the small number of scientists who conceived the idea of the Upper Atmospheric Research Satellite, UARS. And he has served as a consultant to the space program of the People's Republic of China. And he was an associate editor of the Journal of Atmospheric Sciences. And in his career, so another aspect that I would like to, in the same category, is that if he receives a request to review a thesis from a developing country, then in spite of his set schedule, he would do it. He would never refuse such an invitation, and he would give it the same attention and write detailed suggestions and responses as he would do any other thing. And he has, in his career, graduated 18 PhDs, and many of them are distinguished scientists in their own right. And I would mention one of them. One of his students, Susan Avery, is now the director of Woods Hole Oceanographic Institution, which is the lead oceanographic centers in the world.
Second lead.
And so with this a brief introduction, and there are many more things to say, I would invite him to speak about his recent work on gravity waves.
I should make one geopolitical correction to Sultan's very nice introduction, and that was I was an advisor to the Taiwan Space Agency rather than the People's Republic of China Agency. There's quite a difference there. Okay. Both in scope and in politics. Okay. This is, I sort of work in several areas. This work is primarily not done with my graduate students here. It's actually done more with a colleague at Goddard Institute of Space Studies and Peter Love, who was a recent postdoc working here. So the idea is, first I'm going to discuss a little bit of the basic physics underlying the need for gravity wave parameterizations in climate models. A lot of you aren't familiar, most of you are very familiar with the need for cloud parameterizations, but not for gravity wave parameterizations. Then we'll look at a climate model simulation without any gravity waves, and then look at how adding now some jargon. Orographically forced waves would be those forced by flow over mountains. And non-orographically forced, well, I'll mention a little bit, that can be forced by almost anything. And then there's some new stuff. So first some basics. Okay. So I see oceanographers here. So we're all familiar with water waves. And water waves, although you don't think of it, you throw a rock in the water, you see the wave, you go to the beach, a wave knocks you down. If you're unfortunate to be in the way of a tsunami, well, don't do that. But basically it exists because there's a big density gradient between the water and the air. And so you have these gravity waves that exist. And gravity waves are buoyancy waves. I have to always, when I give a talk in a physics department, I always have to be very careful to distinguish what I mean by gravity waves. A lot of people show up and then they hear me talking about buoyancy waves and they walk out. Okay, so, but in the atmosphere, we don't have the sharp gradient. We have the density decreasing with height. And so these waves can exist by virtue of these height gradients. Basically, you get pressure differences here, because if it's in this low density, there's very low pressure, and down here there's very high pressure, and comparatively. And here the same thing's true, but in a continuous fashion. And these gravity waves, unlike water, well, they propagate both horizontally and vertically, but there's a lot there that I don't want to go into. And the most familiar thing would be airflow over a mountain. And there's many things that can happen here. First of all, it can have weather implications. It can sort of help propagate weather. But also, one of the more beautiful things is it also can give rise to lenticular clouds in the lee of the mountains, which are truly spectacular. They look like flying saucers. And if you've seen one, you don't see it very often. You have to be quite high topography. So, okay, having said that, I want to sort of walk you through a little bit of mathematics, just because this is a crucial aspect of understanding this. And there's something called the Liouville-Helmholtz theorem number 1. And this is pressure, and the primes indicate the wave variation in pressure. W, vertical velocity, the wave variation. C would be the phase velocity of the wave. U0 would be the wind. Rho 0, the undisturbed density. U prime, the wave, east-west flow. So, and this overbar indicates average with respect to the phase of the wave, so over a complete wavelength. So P prime, W prime is the upward energy flux associated with the wave. Pressure is force per unit area. W prime, it has the units of energy flux. So it's upward energy flux. And rho U prime, W prime is the upward eastward momentum flux. So I'm going to walk you through one of the key results that all of this depends on.
What do you mean upward eastward?
Well, in other words, there's an upward northward too. In other words, it's the momentum flux propagating upward that accelerates or decelerates to the eastward direction.
Upward flux eastward. So the special gradient in the upward momentum?
No, it doesn't have to have a gradient. It'll just carry this momentum flux. A good way to explain it is, this is the way I explain a lot of this, is that from personal experience, the key thing about waves, gravity waves, there are two key things. One is that they propagate energy and momentum at a distance. If you don't believe me, go to the beach when there's a hurricane a few thousand miles away, and the waves will be very great, and they're transporting momentum and energy, same as this equation indicates. But also, it doesn't give up its momentum and energy uniformly. If you're seaward of where the waves break, and you're standing there and a wave comes, it gently lifts you up and puts you down, but it didn't knock you forward. If, on the other hand, you're inside where the wave breaks, then it knocks you down. And so what happens is the transfer of momentum flux occurs not everywhere, but it occurs particularly where the wave breaks. And that's sort of the easiest way physically to explain it to people. So, in other words, when the wave is coming in, there's a momentum flux, and you feel it when it breaks, okay? So, a key point here is, if you have an upward energy flux, positive, notice this is positive, and C is greater than U, in other words, the phase velocity at which the troughs and the ridges are propagating are faster than the wind, then this momentum flux, if absorbed by something, is accompanied by an eastward momentum flux. Now, if it's absorbed, it'll accelerate in the eastward direction, and it'll tend to increase U0, and it will tend to increase U0 towards C. If U0 is greater than C, it'll decrease the wind towards C. Yeah?
I have a question. Why does the wind direction in the south-north have no contribution to this?
Oh, it does. There's a comparable equation where I could put a V0.
Okay.
So, yeah, this is a vector. I'm just giving one component, so I don't have to deal with vectors at this point. Okay? So the key point here is that this theorem implies that gravity wave absorption tends to accelerate or decelerate the flow to the wave phase velocity c. That's a fundamentally important physical characteristic. Now, in the atmosphere, most gravity waves have their source in the lower atmosphere, flow over topography, convection gives rise to gravity waves, and the winds there are relatively weak, which implies their phase velocities would be relatively low. So for the most part, the action would be to decelerate the flow in regions higher up where the wind is greater than tropospheric values, lower tropospheric values. Okay? So let me illustrate some of the important effects. In the winter, the northern hemisphere, we have, this is a stratospheric. In the stratosphere, the wind is westerly from the west. Meteorologists like to use westerly and easterly to confuse non-meteorologists. Westerly, think eastward. Easterly, think westward. Okay? So, in the northern hemisphere stratosphere, we've got westerly winds. In the summer, southern hemisphere, easterly winds. The only reason I have summer, well, because it reverses. So it's northern hemisphere winter I'm talking about here. So gravity waves, as I indicated from the Ilias and Palm relationship, will tend to decelerate the flow because the winds in the stratosphere are greater than where these waves are excited in the troposphere. So you have a drag, you have a drag. Well, what balances this drag? Something has to balance the drag, or else the winds would be brought to zero. Turns out that away from the equator, there's a Coriolis force on this meridional flow. A meridional flow, north-south, is induced. Now, in the northern hemisphere, the Coriolis force on this flow will be in this direction, sufficient to balance that drag. In the southern hemisphere, it'll be the left, the Coriolis force, again, to balance that drag.
So it's the Coriolis force on the gravity wave motion?
No, this is the Coriolis force on the the induced meridional flow. Because, again, you've got this drag, you've got the flow, and if things are approximate steady state, you have to have the drag balanced by something. And so when you think of what can balance it, the only thing that can really balance it is the Coriolis force on an induced meridional flow away from the equator. Near the equator, that doesn't work, and that's why you get these funny oscillations, these quasi-biennial oscillations, semi-annual oscillations that are equatorially tracked, because this doesn't work near the equator.
But the Coriolis force is a result of motion.
Yeah.
It doesn't create motion. There has to be an external force to the winds or somewhere else to create the flow that creates the Coriolis force that can balance your drag.
Right. But again, it's sort of an induced secondary circulation, if you will.
Why don't you orient those arrows? I mean, you've got east and west, but the vertical one.
But it's not vertical, that's
Yeah,
northward.
so, right.
I should have an east and a north,
Yeah,
I suppose.
north.
Okay. So, for example, this is very important because this sort of drag in the troposphere induces this equator to pole circulation, and in the upper part of the atmosphere induces a winter to summer pole circulation. Now, those of you who have taken meteorology know this looks nothing like the Hadley-Ferrel cell, polar cell situation. Why is that? Because this is a Lagrangian picture, not an Eulerian picture. This is actually the path of the air parcels rather than a picture of the winds as a function of space and time. And this is very important in the atmosphere because this induces cooling by adiabatic ascent and warming by adiabatic descent, which accounts for the fact that the mesosphere, the winter mesosphere, which is under perpetual darkness, is much warmer than the summer mesosphere, which is under perpetual sunlight. And so these dynamic effects can be pretty important. They also transport substances, ozone, for example. Those of you who have studied this realize this is sort of the Brewer-Dobson circulation down there. And this is induced by this wave drag type of thing. Okay, so let me show you what actually, so this is sort of underlying principles. So I'm going to go through a paper I published a few years ago, a couple of years ago, I guess it would have been. And as I say, I work at GISS, and with my colleague Tihan Zhou, who got his PhD here several years ago, and the rest of these folks work on the GISS climate model, and working on climate models is a group endeavor. One person knows clouds, one person knows this, the ocean, one person knows vegetation. It's a group endeavor. So hence all these authors. Not quite as bad as experimental physics, though, yeah. Okay, so if I look at era, this is era 40, so it covers this for 20 years. You see that the winds, so okay, so here we have pressure, 1,000 hectopascal, 1 hectopascal. This would correspond to the surface. This would correspond to about 50 kilometers. Equator, North Pole, South Pole, January, winter, summer. As I said, we have westerly winds or eastward winds here and the opposite there. And you see that the winds in the northern hemisphere, you see the familiar jet streams, but up higher there's something called the polar night jet. And the polar night jet's about 45 meters per second, and then there's a summer circulation. If you do without gravity, with no drag at all, we actually took out all the drag formulations that were in that model, which meant we had to run it. Those of you familiar with numerical simulation, this is a very expensive run because we had to run with very, very short time steps. And you see the winds are much, much too strong. They don't slope in this direction. They're much, much too strong. These aren't so bad, which tells you something. And of course, the jets aren't affected too much. But they are affected a little. Okay, so this is, well, not a little, just a little different. Now, if I put an orographic drag, this is only the drag that's induced by flow over mountains, topography, and things like that, I then reduce these winds quite a bit, still a little strong, but quite a bit. And I don't affect this, a little bit too. I don't change these a great amount.
That has no wave drag?
No, this has orographic only.
Only.
OG is orographic only. Okay, now I have to indicate that this is in modeling, you tend to separate orographic, you have separate parameterizations for orographic wave drag and non-orographic wave drag. Orographic is easy, it's flow over topography, mountains, things like that. Non-orographic, there's tons of sources. There's convection, there's jet emission, there's fronts, there are all the wind shears, all these things. And they, unlike the phase velocity of the gravity waves launched by orography, flow over mountains is really simple. The phase velocity, the mountains move at 0. So they have a 0 phase velocity there. But on the other hand, the non-orographic waves have a broad spectrum. And so they can do quite different things. That's why they're separate. And also the sources are not well known. I'll remark on that at the end if we have time. Okay?
Mark,
Yeah.
how do the gravity waves then propagate? I mean, you've got orography on your bottom left, and then you're propagating into the stratosphere of 1 millibar without really affecting your lower altitude jets. Is that what you expect?
Well, because they break higher up. In other words, because the density of the atmosphere goes down, the waves would tend to keep the wave kinetic energy, rho v squared, approximately constant. So if rho is going down exponentially, the velocities are going up exponentially, and they'll break and thereby give up their momentum.
Are they in, is that critical, the critical altitudes where the,
Well, there are also critical levels where the phase velocity equals the wind velocity. Those are the two things, wave breaking and critical levels, exactly right. Okay. So now we put in orography, the non-orographic wave drag. Now, this was an illustrative picture, so we didn't try to do it realistically. We put in a globally uniform source of non-orographic waves. We knew it wasn't correct, but by the way, a lot of people still do that. We're putting in a globally uniform source. And you see, it reduced it even a little bit more. It made it look funny. But it's not too bad. Not too good either, but qualitatively in magnitude, quite similar.
So these uniform mountains, what do they look like?
What do you mean uniform? No.
Well,
The non-orographic is uniform. Technically, in the model, what you're doing is within a grid, you're looking at the variance of orographic height, and you're putting the variance within a grid space of the waves. Things get kind of technical because some of the gravity waves are resolved within the model. So we're really looking at the subgrid scale, just like clouds subgrid scale. So, but we're looking at the topography within a grid box.
In the non-orographic contribution, you must be just parameterizing in some way.
Yeah.
Does that have latitudinal, longitudinal?
It's globally uniform at this point. I'll talk about that later.
Yeah.
This paper, part of this paper. See, okay, there's a little bit of tactics in publishing, particularly for the students. Okay? We worked very hard to put gravity waves in the GISS model, but other people had gravity waves, good gravity waves, and everything. How do we publish a paper saying we can do it too? That's not a very publishable paper. So the way I did it was I realized no one had actually explained methodically what the different waves going in do to the model. So that's the way this paper is structured. Okay, so this is the northern hemisphere, January. But of course, and also of course through the thermal wind equation, this affects the temperatures. So again, these are era observations. No drag. Now, by no drag, I mean no gravity wave, no subgrid scale gravity wave, no parameterized gravity waves. There's still the drag from planetary waves and resolved gravity waves and everything else. It just, There's no subgrid scale gravity waves. And you see here, every 5 degrees, this is where the model is too cold. So this is the familiar pole problem, where when you go up in altitude, even not so up, you tend to have the winter pole too cold in climate models. We put in the orographic, it gets better, less too cold contours. And here it gets even better. So it's minus 70, minus 70, minus 70. Okay? But what about July? July, it's even worse, because if we think of planetary waves in the southern hemisphere, I love saying this to my Australian and New Zealand friends, there's basically no land in the southern hemisphere. There's very few mountains. I also insult them by saying there's not many people either. Okay, so because of that, the winds tend to be much stronger. Remember, this is the era. So this is July, so in the southern hemisphere winter. Here we had about 45 meters per second. Observations here are 95 to 100 meters per second, twice as large, the polar night jet. No gravity waves? Well, gee, it's about 300, so it's preposterous. So it's terrible. We put in the orographic, it gets a little better. Now it's only 200. And then we put in non-orographic. Now again, it's globally uniform. And it's still way too high, 150, maybe 160, 170, somewhere around there. So what this experiment tells us that a globally uniform subgrid scale orographic gravity wave parameterization might work. If it works in northern hemisphere winter, it won't work in southern hemisphere winter. And if it works in southern hemisphere winter, it won't work in northern hemisphere winter. If I put in enough drag globally uniform to bring it down to here, the northern hemisphere winds are just killed.
How come they make these 040 so-called observations if radiosondes go only to like 25 kilometers high?
There are these expensive little pieces of metal that fly around the Earth.
You think
And look at satellite measurements.
at 50 kilometers?
Sure.
They see winds?
Sure, not winds. They see temperatures and use the thermal wind equation. Okay. I wouldn't be that nasty to a student, but he's my colleague. I can be nasty to him. Okay. Okay. So the moral here is that a globally uniform non-orographic gravity wave parameterization won't work. If it works in one winter, it won't work in the other winter. Okay? And of course, if we look at the temperatures, it's even worse because the winds are worse. It just goes with the thermal wind equation. So here's the observed temperatures. Now it's down to minus 90. That's observations. But here it's much colder. Look at all these contours. It's way too the cold pole problem is much worse. Orographic, a little bit better, but still lousy, and still pretty lousy. So again, that's the moral. Now, we did produce one decent result in here. And here, if you remember, I'm not showing the observations, but remember, this looks pretty much like observed. This looks pretty much like observed. And these are model results. These are the temperatures, and you see very little. This is a 5 degrees off contour. So we've practically got the temperatures pegged. So how did we do that? We put a notional gravity wave source, which put gravity waves, this is thought of as sort of an ITZZ, convection launching gravity waves, and then a winter source, which is thought to be either a jet emission or frontal winter launching gravity waves.
So what's contour?
But we just made this up, yeah.
What's contoured here?
This is the momentum flux at 100 hectopascals.
Vertical momentum.
Vertical momentum flux. Sorry about that. But we basically notionally took convection and this. Now other people are already putting in some physical. We want to too, if I'll ever let my student My colleague back into NASA right now, hasn't been allowed for 9 months due to a snafu and being deemed a security risk until they finish this. Okay, so, but my bias, I'm an old-fashioned guy. I don't want to put stuff in until I understand how it works. So I want to specify it and understand the sensitivities before I turn the model loose to do whatever it wants to. That's just me. So, okay, so this is actually, so about halfway through, a little more. This is with the title of what I'm talking about. And this was just published, well, a couple of months ago. And in Journal of Climate. Both papers are in Journal of Climate. And this is a result of a workshop at the International Space Science Institute in Bern, Switzerland. And the interesting thing is, I do modeling, and believe it or not, look at observations a little bit. I'll talk about that a little later. And Joan Alexander looks at satellite observations and also develops parameterizations. Peter Love was my postdoc here, and he works at NCAR, Germany, Jülich, and he works in France, and she's in Germany, in Tokyo. So there's a bunch of modelers, a bunch of observational people, and literally for the first time, trying to compare gravity wave momentum fluxes in models and those derived from observations. See, up until this, it's kind of fun because you do everything else, your radiation, your boundary layer, all your treatments, and then if it doesn't work, you just put in a drag to make it work. So now, we're actually doing something dangerous. We're actually kind of trying to constrain it with observations. And the observations, the satellites, this is pretty tricky. And satellites, you've got limb scanning satellites go up and down. You look for temperature fluctuations. You drive vertical wavelength. Look at the next profile and look at coherence amongst vertical wavelength fluctuations. By looking at the horizontal picture of the coherence, you can get an indication of the horizontal wavelength. And then you use what's called the polarization relations to derive momentum fluxes. Long duration superpressure balloons, when you're putting a balloon up around 20 kilometers and you're measuring the horizontal fluctuations in winds, temperatures, so it's direct, vertical fluctuations. And the other thing is, it's a Lagrangian measure. The balloon is going along with the air, as opposed to the Eulerian picture. And then, of course, those of you who are new don't realize, but I've been the custodian of US high-resolution radiosondes for several years, so we're doing this. Now, this can only get absolute momentum fluxes because it's getting temperature fluctuations, but it has no idea which way they're propagating. So what I mean by absolute fluxes is it would be the momentum to the flux to the east, plus that to the west, plus that to the north, plus that to the south. I'll talk about that a little bit later. Whereas these methods, you can get vector fluxes. The vector fluxes are what appear in the equations of motion. Okay?
So what is the satellite actually measuring?
It's measuring radiance, but deriving temperature from the radiances. And the models are of 3 types. Climate models with gravity wave parameterization, Hadley Center, ECOM, Hamburg. Our version of the GISS model, this is very different from what's used in AI4 and 5, by the way. And these are very high resolution, not very from a weather prediction viewpoint. This Kanto model has about a 60-kilometer horizontal resolution. The CAM5 has a 25. But the vertical resolution of Kanto is 300 meters, which is not usually used in climate models. Now, let me mention a little bit about absolute momentum fluxes. This is actually from the ECOM model, January and July. So if I look at the absolute flux would be, this would be the east-west, this would be the north-south. Excuse me, what is dashed? So this would be the north-south, and this would be, solid line is the absolute momentum. Yeah. But if I look at the latitudinal variation of the absolute momentum flux and the actual momentum flux, you see, you get some indication like it's big here, but you don't know its sign. So the absolute momentum flux is not perfect. It's not a perfect measure, but it's all we can get from satellites at the present time. So what do these observations show you? Here's the comparison from two different groups from the hurdles on Atlas, on the Aura satellite, Sabre, another satellite, time satellite, and this Vorkor is these constant pressure balloons, but it's only at 20 kilometers, and it was flying in Antarctic latitudes, so it's down here. So this is what it shows. What are its main features? Main features are that the maximum momentum fluxes, again, January and July, are in winter, high latitudes. The momentum flux isn't maximum on the equator, where we might have expected from the ITCZ. It actually looks to be at about 20 degrees latitude in the summer hemisphere. So already is a little bit of a surprise there. Okay. And the other thing I want to point out is that in the summer hemisphere, the momentum fluxes seem to be going to zero. They're decreasing in the summer hemisphere. What do the models show? The colors don't show up well. I'm not even sure I can tell you which is which from that. But there's the econ model, GISS model, Hadley, and these two high-resolution models. And again, they're showing maximum momentum fluxes in winter high latitudes. In winter high latitudes. And the ones that CAM5 and the Kanto are showing a little bit of maximum at that 20 degrees. But the others aren't. Again, the one I showed you, we have, in the GISS model, we have that notional jet ITCZ gravity wave source. The others are globally uniform. They're non-orographic gravity wave sources. And certainly, in the summer hemisphere, they're not going to zero. And clearly, this is a function of the way they're specifying their sources. If it's globally uniform, why should it go to zero at the pole?
The biggest discrepancy between models is at 20 kilometers. Is there a reason to expect
Well, there's not. The main discrepancy is this CAM model is very low throughout. CAM has 25 kilometers horizontal resolution, but it has very coarse vertical resolution. It's just a CAM5 at very high resolution. And technically, they've set up the numerics to give a sponge layer at around 2025. So we're in the sponge layer. So part of this exercise was people didn't realize how badly the high resolution models compared with one another. But that's another subject to be explored. But again, it's showing the high sources. It has to, because all these models are relatively mature. The GISS model, the ECOM, and the Hadley model. And they wouldn't be publishing them if the winds didn't have rough agreement with observations. So you put in the drag that you need to make it look respectable. So that's why they kind of agreed, I think. This was a surprise. If we took the globally averaged absolute momentum flux, now here we took the model momentum flux, eastward, westward, northward, southward, summed them up to get we couldn't get the vector momentum fluxes from the satellite, but since we have the vector momentum fluxes in model, we could just derive the absolute momentum flux in models, okay? And what we note is These are the satellite ones, except for CAM, which is an outlier. And these are the model ones. And these are scale heights that just e-folding. But basically what you see is that the satellite momentum fluxes are falling off with altitude much faster than the momentum fluxes in the models. And the ones with the parameterizations are these, and this one's sort of in the middle, Kanto. So, and that we think is, remember I said that the non-orographic gravity waves are sort of broad spectrum. They can have a variety of phase velocities, wavelengths, etc. But anytime you're observing, you can only observe within a window of wavelengths, frequencies, whatever your technique is. It's got a limit of a so-called an observational window. And if you're looking at a broad spectrum phenomenon like gravity waves, these waves can float in and out of the window because of observational constraints. I don't know if that's clear, but you know, it's sort of something you got to put up with.
So there's a much bigger divergence in momentum flux in the observations, d by dz.
Well, yeah, one of the colleagues at one of those meetings derived this to get apparent accelerations, but that's nonsense because they're falling off for some other reason. In other words, if they're falling out of an observational window and their amplitude is going down because they're falling out of an observational window, that doesn't mean they're not having an effect on the wind. Okay? Okay, so this was also a challenge. Peter was very innovative in this. We had to figure out how to display these. And remember, these gravity waves are falling off at different rates in the models and the observations. So we experimented, and on all of these, the number is the globally average momentum flux. This is at 40 kilometers and July. And we did it for 3 years. This is July 2006. So this is the globally average momentum flux. So at 40, these models, the satellite observations are falling off. So you see this number is smaller.
Sorry, satellites are on the left?
The satellite Sabre, hurdles, model, 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 and these are the high resolution ones. So the fact that these are smaller, we've absorbed, but we wanted to show the geographical features. So we didn't, if we just did it linearly, then you'd have, where it fell off fast, you'd get nothing. So what we did is we plotted the log 10 of the factor to multiply the globally average momentum flux to get the actual derived momentum flux at every point on that map. And again, July, we see observations, a maximum, and the winter high latitudes, models, winter high latitudes, so that agrees. The observations showed us 20 degrees summer maximum, a little bit here, and you see much less of that in the models, or maybe none, except the high resolution one does tend to show it.
So those three blobs, equatorial blobs, is that hard to see? That's due to the land masses.
I'm going to show something about that if I have time at the end. That's some very, really recent stuff that hasn't been published. Okay? But notice this summer high latitude, the summer high latitude stuff in Hadley and Econ is not observed in the satellite. So that summer max is what I showed on those zonally average plots, that it should fall off to 0, but it isn't. Okay? Now it does in our GISS, but that's because I made it. I just specified the source. So this is using the fluxes over Antarctica for, there was a campaign with many, many high altitude balloons. measuring gravity wave momentum fluxes from Vorkor. And they found, for instance, very high momentum fluxes over where the tip of South America hits Antarctica with its high topography. Okay? But CAM5, okay, here's a little dirty secret we didn't know until this workshop. These workshops are very valuable. Kanto doesn't have an orographic gravity wave parameterization. CAM5 does. And I asked Karasato, why not? Why doesn't it? He said, well, it didn't work when I put it in. So there's a little pragmatism in all this stuff. But even the high resolution models are under resolving the topographic gravity wave sources. We can see that also with the high resolution radiosondes. This was done here by us. And you see in July, you see a signature of the Rocky Mountains. This yellow is higher than the green. You see a signature of the Rocky Mountains. But you don't see much in the satellites, you don't see much in the models. So they seem to be underrepresenting the effects of topography. So some conclusions from this part. Then there's one little thing afterwards. Different methods for deriving gravity wave momentum fluxes from the same satellites give some, I didn't go over that. Remember I had a hurdles 1 and hurdles 2? Well, the hurdles 1 and hurdles 2 are using the same data, but making somewhat different assumptions. Remember I said they look for vertical wavelength fluctuations and look for coherence? Well, one of them, if they don't find coherence, they throw it away. And the other, they keep them all. So that would correspond to averaging over your strong events in one case and averaging over strong and non-existent events in the other case. So even the same data gives you, your method of analysis can give you different results. By the way, that's sort of why I was a senior author of this paper, because these groups that were disagreeing, they couldn't have one of them be senior authors, so I was sort of seen as a harmless, impartial person. Okay, so these satellite fluxes fall off faster than the climate models of gravity wave parameterizations and Kanto resolved gravity waves. Kanto was built to resolve gravity waves. An important point is, there's a great stress in horizontal resolution, and you think they'd resolve gravity waves, these small scale stuff. But if you don't have fine vertical resolution, you're not getting proper vertical propagation of these waves, and you're certainly not getting interaction of the waves of the mean flow. So focusing just on horizontal and not on vertical is a bad idea for these things. Yeah?
You said the Kanto model had no orography in Antarctica.
No parameterized.
Oh, okay.
It still feels it in the model, sure.
Okay.
Okay? And again, we think this is due to this, that falls off faster as that. And they all get maximum winter high latitudes. They don't show, the ones with constant non-orographic source specifications do not show that fall off at summer high latitudes. There's local maximum over tropical continents, and even high resolution models don't resolve orography real well. So in that paper, it said some future directions, since a lot of these flaws were due to that constant gravity wave source, would be improvements in specification of these gravity wave sources. And also, there's a group in Europe trying to design a satellite to observe gravity waves better. Okay, now, I've explained a little bit. For the last 10 months, my colleague Tihan Zhou has not been allowed on NASA computers, and not allowed in the last 7 months or so, not allowed in the building. And that's because there was a bureaucratic snafu. So he fell off the database and now has to go through a complete security check. And of course, our friends in mainland China are our very great friends, but they're also suspicious when it comes to security concerns by government agencies. So there you go. So he's not been allowed. So I quickly tried to cook up something we could do while he couldn't use NASA computers and get in the building. So I decided to look at something like this. And that is, in the non-orographic gravity wave parameterization, we want to look at convective forcing of gravity waves. And there's a couple of groups that have done that, and they based it around latent heat release. And an early work by Rind based that formulation on in-cloud vertical mass fluxes. So one's mechanical and one is latent heating, if you will. Now there's another paper by Favela et al. Where he used a storm model with moisture, got gravity waves, and then took the mechanical forcing from that moist model and put it in a dry model and got essentially the same gravity wave response. So he concluded that the main forcing was this mechanical oscillator. The updrafts just varying, just a mechanical oscillator. So we decided to look a little, and of course, well, let me skip these. Basically, these are just to show that the Barris and Chun and Bayek tends to get their maximum fluxes in the ITCZ region where the latent heat release is the greatest. So what we decided to do was to look at precipitation rate. We had 3 months of these gravity wave momentum fluxes, and to look at the latent heat release, which is very essentially rainfall rate, gives you latent heat release. And for January 2006, which would be the latent heat source to a certain extent. And this is cloud top pressure because the very high clouds are probably having more mechanical oscillator effects. We can't measure the mechanical oscillator by any means I know. And these are the absolute momentum fluxes. Now this is no longer the log because I'm not looking at things at different altitudes. I'm just looking at one altitude, which is at 20 kilometers, okay? And you see in this ITCZ region, I don't see much gravity wave momentum fluxes. I see the gravity wave momentum fluxes maximizing here, here, here. But the high clouds are also maximizing here, here, and here. Of course, the high clouds are also coincident with regions of latent heat release. But the opposite isn't necessarily true. That regions of latent heat release, high latent heat release, aren't necessarily equivalent to regions of high clouds. My colleague Marat will tell you this is sort of well known in the community that the ITCZ releases a lot of latent heat, but it's kind of lethargic, lazy convection, whereas the stuff over continents gets sort of explosive convection. So this would be January, and this would be July, the ITCZ convection, cloud top pressures. And again, you don't see so much, but you do see the high clouds. Well, there's not very high clouds there, but you see a little bit there. It's not as clear for July. Now, there's a complication that I have a colleague, Joan Alexander, will be visiting, and you've got to worry about observational windowing again. Because if you look at the satellite orbits, they're cutting through the equator in a north-south direction, whereas at higher latitudes, they've got more of an east-west. So there's a bias towards visibility of gravity waves that have their propagation in the east-west direction, which will discriminate against the equator. But this is where we are. And that's it, okay? Thank you. So, if I didn't lose everybody, I could try to answer questions. John?
Yeah, Marvin, it looks to me like if your model simulation in the southern hemisphere, the initial model simulation without your gravity wave parameterization is much, much worse compared to the northern hemisphere. But your gravity wave parameterization actually improves that simulation. It's just that your initial simulation is horrible. So to me, it looks like the model's missing. You see what I'm saying?
Well, basically, Edmund Chang has been looking at storm tracks here. And he will say this, the storm tracks appear to be much stronger in the southern hemisphere. The winter storm tracks in the southern hemisphere appear much stronger in the northern hemisphere. So I didn't point that out, I could, that the source in the southern hemisphere is about 3 times as large that we specified. It's about 3 times as large as the as it is in the northern hemisphere. So that's what did the trick. See, when we specified the sources, now we just specified it, well, I don't know what's going on. Okay, we specified that the source here is about 3 times as large. So this is a specification, but we would say that the southern hemisphere non-orographic gravity wave sources are much larger. The winter non-orographic high latitude sources are much stronger in the southern hemisphere. You can fly your plane and test that hypothesis. See how much you can shake it.
Yeah, right.
Okay. Okay. Yeah.
You talk about an even distribution of your non-orographic waves. Wouldn't our waves really even approximately evenly distributed, or are they mostly over land or mostly over water, or?
Well, when we think of what the sources are, the orographic ones are non-even, and they're in the model non-even because of that variance I told you about. Convection is a source, that's certainly not even. Jets or fronts, that's certainly not even. So, and the emission from jets is a problem that's just getting a lot of attention from what I can see. There's been a misconception, part by me till recently, and that is I thought that that was sort of a Rossby adjustment, a momentum Rossby adjustment problem, but it isn't. In momentum Rossby adjustment problem, you know what it's adjusting to. It's adjusting to a geostrophically balanced state. A jet emission is not adjusting to a balanced state. It's just emitting from a jet. And that work is actually just, I think, very immature at this point, but quite important. Frontal collapse, also, frontogenesis also matches gravity waves. These are non-uniform characteristics.
But are the oceans different from the continents?
Well, yeah, they're wetter, for instance, yeah, but also less mountains. But the distribution of convection is different over oceans than over land. The clouds don't tend to get as high, except hurricanes. But I mean, when I moved to Illinois, I was shocked how high the clouds got. But they don't get that high over oceans, for example. Fronts, I don't, Brian, are fronts as sharp over the oceans as they are over land?
Yeah. Okay.
What?
Yes, especially at upper levels.
Yeah.
In the storm tracks.
So, you know, the fronts probably, they're probably similar, but there are definite differences. Should I call you? Yeah, okay.
Yes, yes, Mark. It's a great talk. I need to review all the dynamics of the gravity wave. But anyway, question is, for the no GWT models, I'm thinking if it's probably better to do not include any geography at all.
Well, wait a minute. Well, first of all, let me say that I know of no state-of-the-art climate model or weather prediction model that does not include gravity wave parameterization at this point in time. And now there's just been now initially they just put in the orographic because of the work of Tim Palmer and Norm McFarlane to get the jets right. But now they realize that the non-orographic gravity waves should be included. And I know NSEC is looking into this, but we don't quite know how to do it at the present time. Does that address your question?
Yes, right, actually, right. Another one. sorry,
Sure.
about the southern hemisphere winter, it's either because the Andes mountain, that's only one, pretty high and pretty far low, or it had to be parameterized in any model.
Well, I showed two things. I showed that the models were not getting the very sharp topography quite right by comparison with Walcore and the high resolution radiosondes. So that's probably true. And by the way, sorry to deviate, parameterizing, you'd think parameterizing orography is easy. You just flow over a mountain. But that's not true. If it's not a mountain chain, how much flows over the mountain? How much goes around the mountain? You know, that depends on stratification. So even that's non-trivial. But the non-orographic is something else again. And you're getting into dangerous situations here because convection itself in a climate model is parameterized. So now you're going to build a parameterization based on another parameterization. So this has to be done very carefully comparing with observations in my opinion.
Yes, but Jaime, do you have a question?
So, the first part you compared the ERA 40 with the models, and recently there are some very high resolution geoanalysis, ERA interim or CFS geoanalysis. Do you think the results will be changed if you use more?
Not on these large scales, no. I mean, we use the NAR for other reasons. Shumay is doing that. But for the large scale, no, I wouldn't expect it.
So Bob,
Among the, you said almost all of the models now have non-orographic parameters.
No, they have orographic.
And how about non-orographic parameterizations?
Hardly any.
Hardly any.
Yeah.
And
The
are
ones
those
that go high have to.
Are those that do have that parameterization, do they assume uniform parameterizations globally?
Some do, some don't. Now, let me enlarge on what Bob said, because now we're moving into a chemistry climate models. So if you're getting the polar temperatures wrong, and you've got temperature-dependent chemistry, then why spend the money? So those models have had to have parameterizations of some sort in to get the temperatures reasonable, or else you'd have to make up fictional reaction rates to make up for your temperature errors, which is even more deplorable. So yeah, they're getting put in models now.
There's observational data that you never mentioned from polar regions where people have made simple photographs of night glow and things like that. How useful are those?
There are other observations, as Bob says, from air glow, from radars, of gravity waves. Here, the emphasis, since we're emphasizing the word climate models, ones that would give some sort of a climatological, geographical distribution of monthly averages, things like that. So there are some observations, you're quite correct, we didn't put in because you had to be able to derive momentum fluxes, and you had to do it over a broad geographical region and get monthly averages, characteristic monthly averages.
Well, especially for the polar regions where you don't have much satellite data or don't have any satellite data, they could be fairly invaluable, wouldn't they?
You tell me how you get gravity wave momentum fluxes from these pictures.
Well, you get wavelength, you get altitude,
Right,
you get,
right.
and you get propagation times too.
Right,
So I
right.
don't know whether you can derive enough from that.
I don't know either.
so Brian has a question.
Yeah, well, I mean, this is interesting. I mean, coming up from a different scale perspective, working on the mesoscale community, I go to a lot of talks where they show that models, if you run down less than 10-kilometer grid spacing, you get beautiful mountain-induced gravity waves, wave breaking in some of those critical South American regions. I think they're even having a field experiment this winter and so forth. So when you're saying high resolution is even having difficulty, I mean, I think that was at, what, 60 kilometers?
High resolution climate models.
Climate model, yeah. Well, that's the issue here. What it's relative what high resolution is. And I guess my point is that observations have limitations, models have limitations, but you can imagine a situation where if you had enough computer power, which does exist now, you can run a global model at 5-kilometer grid spacing over a long enough period of time to get enough statistics and get the momentum fluxes. To actually work with the observations in a data simulation or some aspect to actually tackle the momentum fluxes instead of absolute momentum flux. You have to actually have the vectors from the model.
Yeah.
I guess my point is I think these models have realistic structures and at least climatological structures that you can take advantage of.
Right, but I think we're still a long way away from climate models with 10-kilometer horizontal resolutions and, say, 300-meter vertical resolutions that extend significantly in altitude. See, again,
That was
getting,
my point.
getting them.
To tune your parameterizations, you're trying to do it in an absolute momentum flux from a satellite.
Yeah.
And you're trying to match that field. That's what some groups are doing. But to understand the full three-dimensionality or the vector fluxes, why not look at a high-resolution model and actually understand what those...
You're absolutely right. There should be greater collaboration between the mesoscale communities and the climate communities. Very few mesoscale models that I'm familiar with extend up to 50 kilometers, say, or higher. So these gravity waves become much more important at higher and higher altitudes. So that's very promising, but they probably have to be specially produced models to have the vertical, horizontal resolutions and altitude extent that would be needed for this problem.
So with this very nice comment, so let us thank Professor Geller for